Let's look at this electrical boundary condition problem. You're given the electric field intensity for x less than 0, the permittivities of the two materials, and the charge density on the x equals 0 plane. And you're to find the electric field intensity for x greater than 0. Let's begin by drawing a figure with all the information. We have developed boundary conditions for this type of situation. But I think it's more instructive and less chance of an error if you just apply the two Maxwell's equations to do this problem, and you can do it rather quickly. Let this be the y-axis, and let this be the path of integration for the integral of E dot dl. The electric field intensity along this side is the y component of the electric field intensity in material A, and along this side is the y component of the electric field intensity in material B. This distance we will call W. The integral of E dot dl along this side is E sub ay times W, and along this side will be minus E sub by times W. The integral of E dot dl along these two sides will have the same magnitude but opposite sign, so they will sum to 0. This integral is equal to 0, so E sub by is equal to E sub ay. E sub ay is minus 5, so E sub by is equal to minus 5 volts per meter. Always work with your fields in symbol form and then plug in the actual values later. So E sub ay is minus 5, and that's what you would plug in for E sub ay. Working with symbols till the end, it's less likely that you'll make errors with minus signs. Everything would be analogous if this was the z-axis instead. So E sub bz is equal to E sub az, which is equal to 4 volts per meter. To get our final component, the normal component, the component in the x direction, we will use Gauss's law. Here is our Gaussian surface. The normal component to this surface is the x component of the electric flux density field in material B, and the normal component to this surface is the x component of the electric flux density field in material A. The surface vectors on the right and left side have the same magnitude but are pointing in opposite directions. We will now apply Gauss's law. Along the side, the integral of d dot ds will be 0 because whatever electric flux enters exits. So there's no net flux leaving the side of our Gaussian surface. The integral of d dot ds on the right surface is d sub bx times s, and on the left surface it's minus, because of the opposite directions of d sub ax and s, of d sub ax times s. The charge enclosed is the charge on the boundary that's inside our Gaussian surface, which will just be the surface charge density times the area, which is S. You can divide through by S, and now we can solve for d sub bx. So d sub bx is equal to d sub ax plus rho sub s. D sub ax is equal to the permittivity of material A times the x component of the electric field intensity of material A, and rho sub s is 2 times 10 to the minus 9 over 36 pi coulombs per meter squared. So we substitute in for epsilon sub 0 and E sub ax, and we get 42 times 10 to the minus 9 over 36 pi coulombs per meter squared. In the problem, we were asked to find the electric field intensities, so we have to divide d sub bx by the permittivity of material B, 2 epsilon sub 0. Substituting for d sub bx and epsilon sub 0, we get that the x component of the electric field intensity in material B is 21 volts per meter. Collecting our three components, we get the final result for the electric field intensity in material B.